Packings can be used to solve an old problem in combinatorics, the so-called schoolgirls problem, which was posed by Thomas Kirkman sometime last century. Here's the problem. There's 15 girls in a class, and they walk from their school to church every day in a special arrangement in 5 rows of 3, and they do this 7 days in a week. Now, is it possible to arrange the 7 walks in such a way that, given any 2 girls, there's exactly 1 row in one of the 7 walks in which these 2 girls walk together? Well, the numbers here are already a little bit of a giveaway. Of course, they have to do a lot with packings. We can identify the 15 girls with the 15 points of our space. Then a solution of the problem is a packing. So there's 7 spreads in a packing. The spreads then correspond to the 7 walks in a week. An elliptic quadric in our space, well, that's basically a sphere, is a set of 5 points such that every line in the space either intersects this set in 0, 1 or 2 points. So let's have a look at what happens in this very special case. Here we see that the edges and the medians of the tetrahedron are secant lines. They intersect the sphere in 2 points each. The diagonals and the medians of the faces are tangent lines. They intersect the sphere in 1 point each. And the circles and the ellipses are exterior lines. They don't intersect the sphere. Planes either intersect the sphere in 3 points or in just 1 point. They never miss the plane completely. So this kind of plane here intersects in 3 points, the 3 fuzzy points. This kind of plane also in 3 fuzzy points. And the remaining 2 planes in 1 point each. So the other 2 planes are tangent planes. And here are 3 spheres in the flat model: green, red and blue. Here's an example of a hyperbolic quadric in this space. This hyperbolic quadric contains 9 points and 2 reguli, the red regulus and the blue regulus. Here you see a hyperbolic quadric in the flat model, and here another one. The Desargues configuration has 10 points and 10 lines. There's 3 points on every line and 3 lines through every point. The Desargues configuration is one of the most important configurations in geometry. It is constructed as follows within a projective space. Start with a point and 3 lines through this point. Draw 2 triangles in perspective, green one and a blue one. Lines that correspond to each other intersect in a point. So here, yellow point. This gives 3 points of intersection, 3 yellow points. And in a projective space like this, these 3 points are always in a line. Now all the points and lines constructed like this form the Desargues configuration. In the flat case, here's a Desargues configuration generated by 2 lines. So 2 times 5 rotations gives 10 lines, and you also see 10 points. This is the generalized quadrangle of order 2, 2. It is 15 points and 15 lines. Every line contains 3 points, and every point is contained in 3 lines. Now, generalized quadrangles are geometries in their own right, and they are defined by a set of axioms. We're not going to go into the details here, only mention some facts that make this particular generalized quadrangle important for our projective space. Let's have a look at a flat model of this generalized quadrangle. This flat model is generated by these 3 lines. As usual, take the 3 lines, rotate 72 degrees at a time, 5 times, and you get the generalized quadrangle. So here it is. I just want to give you an idea as to why generalized quadrangles are called generalized quadrangles. Say you want to draw a circle using only lines of the geometry. So you draw 1 line, then you draw a second line, and then you find you can never get back to the point you started with using a line of the geometries. You can never draw triangles in this geometry. What you can do is complete circles that are quadrangles. So this is the reason why generalized quadrangles are called generalized quadrangles. Now, much more important for us is the fact that this geometry encodes all the information about the projective space. So we have all the points in here, lots of the lines. How do we get the rest of the lines? Take 2 points and construct all the points that are connected to both of them by lines. So you get 3 of them if both points are on a line. Nothing fancy happening here. But you can also do the same for any 2 points that are not connected by a line. So take 2 points that are not connected by a line. Construct all the points that are connected to both of them by lines. Here's the first one. Here's the second one. And here's a third one. This gives 3 points, and these 3 points form a line in the projective space. So starting with any 2 points in the quadrangle, you can construct a line of the projective space, and in fact all the lines in the projective space like this. You can also construct all the planes. There are 15 planes. Start with a point. Associated with this point is a plane, and its points are all the points that can be connected to this particular point. So here's one kind of plane. Here's a second kind of plane. And we have three different kinds of points, so there's a third kind of plane. Now, hiding in our projective space are other geometries that have 15 points, 15 lines, 3 points on a line, 3 lines through a point, like this one here. But this geometry is not a generalized quadrangle, because as you can see, it contains triangles. Not many people seem to know this beautiful model of the Peterson graph, which sits right in the middle of our projective space. You notice that this model looks very similar to the generalized quadrangle we just had a look at. In fact, it results from this generalized quadrangle by removing from it 5 points. Here we do the same thing in the flat model. Remove 5 points from the generalized quadrangle. In fact, those 5 points form a sphere in the projective space. We can disentangle this picture to make it look more like the most famous representation of the Peterson graph.